Hello, Junior Lab Rats. So this is our lesson for soil weathering, erosion, and mass movements, part 2. This will be lesson 8, and it's the second half of the lesson we started last week, and it will be your last of our 2 virtual lessons. Let's go ahead and get started. So first, we're going to do a little bit of a refresher on wearing down and building up. I'll let that play again because it's worth it. All right, so let's again refresh what erosion is. Erosion is the picking up and moving of weathered materials by wind, water, ice, or gravity. Now, what kind of materials are picked up and moved? That would be sediment. Sediment is the material moved by erosion, and it's made up of weathered rock particles, soil, and organic matter. So, reminder again what deposition is. That is the dropping of sediment that has been weathered and then eroded. So while that was a refresher, weathering is the breaking down of rock and other materials. Erosion is the picking up and moving of those materials. The material that is being moved is sediment, and deposition is the dropping of that sediment. So now we're going to talk about mass movements a bit. Now, I know this was a really long lesson, you guys, and yours kind of like sprawled around and covered all kinds of stuff that we will likely touch on again a little bit more. But bear with me, and hopefully we can get through the slideshow quickly, even if the reading may have taken you quite a long time. So mass movements are primarily caused by gravity, and some factors that influence what types of things move and how they move are the weight of the material's resistance to sliding, and seismic activity. Seismic activity would be what the Earth's tectonic plates are doing, and we'll talk about that later this year. But it's things like faults that slip, earthquakes, rumbling, that sort of thing. So one type of mass movement is creep. Creep is the slow, steady downslope flow of loose material. So this hillside here is a great example of creep because you see these little trees have changed the way they're growing. So these trees were rooted right here, and they would grow straight up normally, but in this case, as this material has slid, the tree kind of moved with it, probably actually at an angle. See the way the trunk is? When that stuff slid, that tree was at an angle, but it started to grow back up. So you can tell the slightly bigger tree here probably didn't move quite as much as some of the smaller ones, and that's because obviously they have less mass to move in the first place. So then we have flows. So creep is the slow movement, and then flows are pretty fast. We have mud flows, and this is a swiftly moving mixture of mud and water. Mud is just dirt and water, so I guess it's really a lot of water and some dirt or some very watery mud. It would have to be pretty watery mud to move anyway, because mud can be pretty viscous when it's thick. And then you also have lahars, and lahars are mud flows that follow volcanic eruptions, and they contain ash mixed in with the mud. And then we have slides, and this type is a landslide. Landslide is when material separates from the bedrock, and this is really common on steeper slopes. Creep would be on a less steep slope usually, but landslides are typically on much steeper slopes. So what you have here is basically all of this material breaks loose and just slides down the side of the mountain. And this is a rock slide. Now, a rock fall is going to be different. So again, you have to think about this just like the landslide. It's like a sheet of rock that just slides down slope. And as you can see, there is a highway that runs along the edge of the ocean water there. And it has been completely obscured by this massive rock slide. That must not have been fun to clean up. And then you have slumps. That's another kind of slide. And that's when it's a landslide over a curved surface. So it usually doesn't go quite as far. It's just like a smaller area that is affected. And then our last kind of slide here is an avalanche. And you may not have thought of an avalanche as a type of slide because it's not a landslide or a rock slide. It's not soil or sediment or something like that. It's just snow. But they behave very much the same way. So you've got thick snow that slides from a slope of a mountain when the mass builds up too much or it starts to melt a little. and you have an avalanche. And whoever lives in that little house down there in the right-hand corner is a very lucky duck. And then we have rock falls. And remember, I said rock slides are different. Rock falls are when you have loose rock that tumble down a slope. And whereas a rock slides is like a sheet of rock that comes loose. Rock falls can be individual rocks or a group of rocks, but it's not one giant massive rock like a rock slide. So mass movements can affect people, even Oprah. And this is a video from several years back when there were some wildfires in California, and those can lead to mudslides as the material that typically holds the earth together burns, and then rain hits the area. A lot of that material can then slide loose.
Less than 48 hours after Oprah Winfrey's inspiring speech about equality at the Golden Globes, Oprah woke up to a scene of devastation unfolding at her Montecito back door. Mark Brown has the story.
That's a huge flame shooting into the sky just beyond Oprah Winfrey's backyard. She took this video of the unfolding Montecito mudslide disaster this morning and posted it to her Instagram page. You can see the rain still falling. In her post, she says, "What a day, praying for our community again in Santa Barbara." Oprah then posted a second video of all the mud in her backyard.
This is how deep the mud is. And house in the back is gone.
Oprah also posted this video of a helicopter she says is rescuing some of her neighbors and looking for missing people.
Well, Oprah has some famous neighbors, and today actor Rob Lowe tweeted this: media talking about Oprah may be running for president in 3 years. Meanwhile, as we speak, her Montecito home's a staging ground for helicopter rescues. Priorities, anyone?
Any process that moves sediment downhill is called a mass movement. Remember, we just went over several different types. And then mass movements are, in the end, caused by gravity. So let's talk about water erosion a bit. So water that does not soak into the ground is called runoff. And right here you see an example of some runoff. That's why we have gutters and storm drains built into our streets. Now, you can have runoff occur in several different ways. First, if the soil is super saturated, which means it cannot hold any more water, you can have runoff. Also, if the soil is very, very dry and the water hits it fast and suddenly, like a big downpour, then it's harder for the water to get in because the soil is very compact and there aren't a lot of spaces for the water to fill. So it tends to kind of run off the surface of it. And then the other way is what we see here. It's when you've covered the ground with some other sort of substrate, in this case, concrete or asphalt. And cities in particular have a lot of issues with runoff because there's nowhere for the water to soak in if there's a lot of concrete going on. So we have all these structures and infrastructures that we've built to control water runoff and move water to a location where it doesn't flood the city. And we know this, runoff can create rills. So then rills lead to gullies, gullies lead to streams, streams lead to rivers. You guys know that because we've been over and over it. So now here's a new one for you, tributary. Tributaries are streams or rivers that flow into other rivers. Tributaries are what feed larger rivers. So you can see this little river here is leading into the larger river, and that means the little river is a tributary. Tributaries are important to understand when we start talking about environmental impacts of certain chemicals that can be used for farming and whatnot, and they can run off into smaller streams that are tributaries to larger rivers, and then they can cause larger ecological problems when they affect the wildlife in those rivers or the wildlife that depends on those rivers. So here we are again. Runoff leads to rills, rills lead to gullies, gullies lead to streams, and streams lead to rivers. And then a stream or river that flows into a bigger river is called a tributary. Erosion by rivers. So All right, so through erosion, a river can create valleys, waterfalls, floodplains, meanders, and oxbow lakes. So this right here is an oxbow lake again. We're going to talk about that in a minute. And we're going to see meanders. These are these curvy things, this here, and floodplains and waterfalls and valleys. So here's a valley. If a valley has a sharp V shape, it was formed by erosion from a river. And that's because the rocks and sediment are carried in the fast moving water and it carves down into the land and creates a valley within mountains. Now, if you have a U-shaped, not a V-shaped, but a U-shaped valley, it was most likely formed by a slow moving glacier. So waterfalls form as a river flows from hard rock to soft rock. And as soft rock erodes more quickly, the riverbed then drops, which causes a sudden change in elevation along the riverbed. So right in here, this rock must be much softer than this rock, because as the river just flows along, and you can kind of see where some other places where the river may have been in the past. But as this river flows along, if it were just flowing straight through here, you can imagine it's just flowing straight through here, but this rock is softer. This is going to get worn away faster. So then it's going to come down and kind of a little more lower, and then a little lower, and then over time it becomes an actual drop, and you get a waterfall. So meanders, here they are located on flat terrain. And they reduce the flow speed of water along the river to curve or meander. So again, these kind of follow the lowest points along the floodplain. And when there's something that slows them down, they tend to start to fill up like you could tell it did here. And then they bend and they wiggle all around. And you can see there is an oxbow lake right here. So erosion by rivers. Let's take a minute and have a look here at this satellite time lapse from the mid-80s to roughly 2010s. And you can see how this river evolves and changes over time. So this isn't very long. We're talking a few decades, not thousands of years. First, I want you to notice this little stream here. This would be a tributary of the river. And you can see that over time it sort of changes shape, but you can also see at one point it kind of disappears. I want you to watch closely. You'll see it disappear starting closest to the river and then backward. There you go. And then it reforms and it connects over here. So I want you to sort of watch the shape of the rest of the river. See, it's narrow, narrow, and then it thickened up right there. Watch it thicken up right as this little stream touches it. Right there. Now, that's because there's suddenly much more rainfall. The river is getting thicker, wider, more full, and this little stream fills up again with water from whatever higher elevation is feeding it. And it's going to then attach here because there's probably a downslope right in there that it was able to overcome because there was so much water coming at one time. Now, the next thing I want you to notice is the erosion that's going on in this curve right here. So when you think back to, we talked a little bit, I think we talked a little bit already this year about the concept of lift. Maybe we didn't. I know we talked about it last year in biology with birds. So this is the same idea. So you see how this is a curve here? All right, so you have water and it's coming at this curve at roughly the same rate as it moves along. And the particles in here are all trying to get around to the other side at the same time. But in order for those particles of water and sediment to get around at the same time, those that are on the outside of the curve, so those that are along here, they have to move faster than those that are along the inside of the curve, those here, because these guys on the inside have a shorter distance and the ones on the outside have a longer distance. You can experience this if you and your friend race around something circular. The one on the inside wouldn't have to run as fast as the one on the outside in order to keep pace. So what this causes here is the outside of the curve or the meander, as we're going to learn they're called, it erodes more quickly than the inside. So if you watch right here, you can actually watch it. See that? Watch it one more time. You can actually watch this push that direction over time. So we'll see when we talk about oxbow lakes in just a second that that's part of what causes them. And now I want you to look at one more thing down here before we talk about oxbow lakes. You can see this is an island, and then that completely changes and then it disappears entirely. And again, this is just evolution of lake and river water. And this little lake area here that kind of widens and then spreads out, it's probably a relatively level field area. So this here is an oxbow lake forming, and we're going to watch another great video of this. But it has to do with a meander in the lake, in the river, I'm sorry, and how that meander creates a little lake. So here are meanders, and these are located on flat terrain, and they reduces the flow speed of the water when they hit a meander, or something that reduces the flow speed of the water can cause a meander, and it allows the river to curve or meander. So it's going to curve around. Now you can see right here, this is kind of what we were talking about before when we were looking at the time lapse, but as this water whips around this curve here, the inside has less distance to travel than the water on the outside. So this water on the outside really picks up speed, and with that is force. You can see how it's really eroded this area. And here is a little oxbow lake. And again, we're going to watch in a minute to see how those form. So here it is, an oxbow lake. All right, so you can see how this lake right here looks like it should have been part of this river, but it's completely cut off. And right here, one is likely about to form. So oxbow lakes tend to be U-shaped. Sometimes they're kind of sickle-shaped. And they're lakes or pools that are cut off from a wide meander. And they create freestanding body of water. So if you look right here, what's going to happen is as this piece of the river, this piece here, bends around, as we talked about before, the outside is going to erode faster than the inside. So as this erodes into here, it's going to cut into this. Also, this one is doing the same thing. This branch, this little bend of the meander, is eroding back. So these two pieces are eroding towards each other. And when they connect, it will be much easier for the water to just go this way than it would for it to go all the way around. So it will continue to dig its little river trench as it goes this direction. And what that will do is sooner or later, the edges here that we're touching will dry up. Either there'll be less rain and they'll start to evaporate because there's nothing feeding it, right? It's a lake, it's not a river. So if it doesn't rain in it, it doesn't get full. So eventually it gets cut off and then it looks like this, and that's an oxbow lake. So here we're going to watch one form. I think it's kind of mesmerizing to watch, actually. And if you look at this image, you can actually see where some other lake patterns may have been in the past. River patterns may have been in the past. So fill in the blanks. You've got your meander here, your waterfall here, and your oxbow lake right there. Deposits by rivers. What do rivers deposit? Sediment. So rivers flow, and when they reach level terrain, they start to slow down. They flood their banks, and they also can slow down when they enter bodies of water, like other rivers or ocean or lake. And when they slow down, they tend to drop a lot of sediment. Sometimes they just leave these incredible artifacts behind. This is called an alluvial fan. So it's a triangle-shaped deposit of gravel, sand, and even smaller pieces of sediment, such as silt. And the sediment as a group is called alluvium. So if you look right here, clearly there was a river here at some point. There might even be, I can't tell if this is a particular sediment that's a lighter color or if it's maybe water reflecting the sun, or it could possibly be even some ice. But one thing I'm pretty sure of is looking at the tops of these mountains, they're very snowy. So that means they've got some decent elevation, and it probably gets pretty cold in this area because some of the snow is down fairly low on the mountains. So in the wintertime, more snow will build up. Now, in the spring, it might not all melt. There might still be some snow caps, but a lot of it's going to melt. And as it melts, it's going to come down the mountain into this valley, this river valley, and pour out onto this plain area here. And this creates the alluvial fan. Now, when you think of an alluvial fan, we're not talking a fan like the kind with blades that spins around. We're talking a fan like the little old-timey ones that you unfold in your hand and wave. That's the kind of fan we're talking about. So another thing we're talking about is a river delta. So this is a landform shaped like a triangle, like this, sort of like the alluvial fan, but this time it's where your river meets water, whereas the alluvial fan is where your river meets land. So if you remember, our Greek letter delta is the letter D, and we use it to represent change in science, but it is shaped like a triangle. So that makes sense. That's what this is. So you're not looking necessarily at this area, but the outline shape here is a triangle, and that's the delta. And their deltas can be really large. This could be a smaller delta, part of a larger delta. And we'll see a picture like that in just a second. So this is created by the deposition of sediment that's carried by a river and enters slower moving or stagnant water. Stagnant means it doesn't move at all. So deposits by rivers. When a river leaves a mountain range, it creates an alluvial fan, and when it reaches a when it reaches a water instead of land, it creates a delta. So this delta right here is one of the larger ones I was talking about, and it's actually composed of a lot of kind of smaller channels because this area probably gets a lot of water that comes and goes. So if you look right here, this whole big thing is a delta, but within this delta, there are smaller deltas. There's probably one right there. I'm sure there's some underneath my little thing here. There's one right here, you can see. So these are deltas where water reaches water. Groundwater erosion. So here is some really cool stuff. Now we've kind of moved on from the whole mass movement idea now, and now we're just kind of touching on other types of erosion. And so the junior class is going to spend a little more time on this sort of thing, and the senior class has got some other stuff going on, and we're going to kind of group up again, but we separate a little bit at this point in our lessons. So what is groundwater? Well, when rain sinks into the ground, it becomes groundwater, obviously. So when groundwater mixes with the carbon dioxide in the environment around it, however, it creates a weak acid, and that acid is capable of dissolving rock. In particular, our concern would be with limestone. And this is obviously a limestone cave that people can visit because they've got rope lighting up here. So it's like time to party, I guess, rope lighting. So let's talk a bit about stalactites and stalagmites. So stalactite is formed when water containing dissolved calcium bicarbonate, which is coming from limestone, drips from the ceiling of a cave. So you got to think about this. The ceiling of this cave is made of limestone, and water seeps through it. And as it comes through and it starts to drip, it's a little bit acidic because it's mixed with some of the carbon dioxide in the atmosphere around it, atmosphere environment around it, and it has become slightly acidic. So it dissolves that little bit of the rock, and then it starts to hang like a little drop, and some of it's going to drop and some of it will evaporate a little bit, and some of the water gets sucked back into the limestone. And this water may be coming from above, like I said, but it also could be coming from below if there's condensation. So as water comes into contact with air, some of the calcium bicarbonate precipitates back into the limestone, and it forms a tiny ring, which elongates to form a stalactite. So sooner it just builds after time. More and more builds up. And this is the opposite. This is a stalagmite. So instead of coming from the ceiling, these come from the floor up. And this is as it drips, drips, drips. It makes a wider base typically than a stalactite would have, but they gain mass or grow at roughly the same rate. So This, you have it dripping from above and landing here. Here's a small one just starting. This one obviously has a pretty steady drip for a long, long time. And these guys, oops. And if you've ever been to the beach and done the thing where you mix sand with a lot of water and then you hold it in your fingertips and you let it drip, you can make like a little drippy castle. My uncle used to call them drizzle castles when I was a kid. This is the same concept, exactly how they grow. So here's how you remember stalactites and stalagmites. Stalactites, these are different mnemonic devices. You can use any and or all or none. They hang tight. They hang down like tights on a line. That goes for people that actually do laundry on a clothesline, which aren't very many people anymore. And you must hold tight to do chin-ups off the ceiling. Stalagmites, they might bite if you sit on them. They might reach the roof, and you might need to do push-ups, and that would be off the floor. So sinkhole. A sinkhole is a giant hole in the ground. Sometimes they're smaller, but they're usually pretty decent size. This one here was massive. And this is when the water dissolves enough of the surface rock that that is often limestone. And then when it's eroded or worn away, it collapses into the cavern beneath it. And that's all carried away by underwater channels and underwater rivers, or it just falls into the bottom of this giant pit. So this one may not look real. There are actually some pictures of it that look even less real than this one here. But this is an actual sinkhole that happened not that long ago in a major city in Guatemala, and it's right there at an intersection. So the placement of it was odd, considering it was right in the center of an intersection, and it was almost so perfectly round that a lot of the aerial photos of it looked almost like CGI. So underground water is called groundwater. That one wasn't hard, was it? And again, you got your party lights here. Party in the cavern. So let's talk about the force of moving water. So we talked a little bit about the force of moving water within a meander and how that impacts the shape of a river. So now let's talk about how water has energy. So moving water has energy, and energy is defined as the capacity to do work. Capacity is like, it's almost like an ability. That would kind of be a synonym, sort of. And work is force applied over distance. So if I move something across the table by pushing it with my finger, that's doing work. But even just moving my finger from bent to straight, that's also doing work, because there was a force applied for it to move, and it went over a distance because my finger actually, like the tip of my finger, moved from one position to another. So work is force applied over distance. Now, potential energy is one type of energy possessed by water, and this is exactly what it sounds like. It has potential, which means it's stored. It's not in use yet. So this, a great example would be a dam. So this dam is holding back all this water. So this water has massive potential energy. Imagine how much force there is with that water. So there's a lot of force, but it's not going over any distance right now, is it? Because it is stuck behind this dam. Force over distance, you can see work being done. So if this dam were to suddenly collapse, there would be distance with that force, and the work being done would be the movement of the sediment as the water goes by. So again, this is because water has energy. And the other kind would be kinetic energy. This is the other type of energy that water possesses. And kinetic energy is energy of motion, or energy in motion. So this is a water wheel at an old mill. And the way these worked is sometimes these water wheels on a mill would be like stuck right down into a moving river or a stream. But very often what they would do is they would build a sluice. That's what this is. It's like a little man-made channel, and they kind of steal water off the side of a river or a stream and reroute it so that it comes and drops in the perfect spot to turn the water wheel. And that water wheel will turn, and as it turns, this axle turns, and then it tends to turn some gears inside the mechanisms in the mill, and that's how they would grind grain. Now, energy, remember we said it is not gained or lost. It only changes form. So all of this water, this water is coming from somewhere at a higher elevation. Otherwise, it wouldn't flow, right? Because it's going to flow downhill due to gravity. So that water at a higher elevation is going to have more potential energy than water at a lower elevation because of gravity's effect on it. So if that water were behind a dam, it would have had potential energy. But while it's moving, it has kinetic energy. And here, as it falls, it has kinetic energy. And when it hits here, some of the energy from that water is going to go back down into the water as it continues to fall. And some of it is going to be transferred to this wheel. And this wheel is going to turn. Now, this kinetic energy here it's a type of mechanical process going on, and it's going to cause this big axle to turn, and you're going to get some heat as it turns, and that's friction. So some energy is going to be lost here, but then it's going to go in here, and it's going to turn some gears and other things, and that kinetic energy is going to be used again in a mechanical fashion. And if it grinds up some grain, then maybe that grain could be made into bread, and that bread would provide chemical energy for whoever eats it. So an object that can do work has energy. Potential energy is stored, and kinetic energy is that which is possessed by moving objects. So how does water erode? Well, water erodes by sediment mainly. So rivers erode and deposit sediment, and slides can dump sediment into a river, like a rock slide or a landslide or a mudslide. And rivers can also erode by abrasion, and this also involves the sediment. So abrasion, we talked about abrasion a little bit with glaciers before, and how items that are picked up by glaciers are scraped along the surface. And you can think of that like sanding, like you would do with a sanding block or sandpaper. You would scrub it over the surface of something. This kind of abrasion is a little bit more like sandblasting, but instead of with air, it's with water. And the reason that is similar is that both air and water are fluids. And although one is gas and one is liquid, they're both fluids, and they both follow the same basic laws of fluid physics, fluid mechanics. So as this river flows, it's going to carry sediment over these rocks, and it's going to scrape and weather the rocks as it goes. This is why river rocks are so smooth and slippery when compared to rocks that you just find sitting on land. The water itself moves and dissolves things on the surface, and then you've got the sediment within the water rubbing against the rock, and they make them perfectly smooth. And then they carry away those pieces they've broken down further down the river, because that is the process of eroding. So river sediment load is the amount of sediment that it carries. So the bigger pieces of sediment are going to roll and bounce along the riverbed, and the smaller pieces are going to be suspended in moving water. So think about what this sounds like. We talked briefly the other day about wind erosion, and we talked about how the larger pieces are going to move across the bottom by saltatory movement, and the lightest of pieces were going to get carried up into the air and move around within a dust cloud because they are suspended within the fluid of the air. Well, these are smaller particles of sediment are going to be suspended within the fluid of the water in a river. So a river erodes the surface by picking up and moving sediment. How much sediment a river carries is its sediment load. The scraping of the bottom and sides of a riverbed by sediment is called abrasion. So erosion and sediment load, we'll talk a little bit more about sediment load and how it affects erosion. So a river's slope, volume of flow, and its shape affect its shape of its stream bed, affect how fast the river can flow and how much sediment it can erode. So how much erosion a river can cause depends mainly on how much sediment the river can carry. A fast river causes more erosion than a slow river, and a river with rough water causes more erosion than a river with smooth water. And that should be pretty obvious, all of that. And you can tell by looking at this picture of this little stream bed that the water is not always this low, because these rocks here and these here are fairly smooth. So at some point they've had water with sediment rushing over them, at least enough to smooth out the rocks. So let's talk glaciers a bit. Now, when glaciers do this, when they break off big chunks like that, it's called glacier calving. And there are some really great YouTube videos of it. Some almost get a little scary because giant chunks fall off, and usually the people viewing it are in a little boat and the boat starts rocking really hard because they create huge waves. Look at the, see how it hits the water like that. It's going to create a big ripple effect, big waves. So a glacier, we know, is a large moving mass of ice, and that during the ice ages, glaciers covered most of Earth. Now we have two different kinds of glaciers mainly. We have valley glaciers, and this is an example of a valley glacier, and obviously it's going to fill in the valley in a mountainous region, and it's going to carve that valley as it travels. And you can see here, this little bit right there, there's some melting at the edge of the glacier, or maybe slightly underneath, and it's formed a little waterfall on its way down. And then continental glaciers, these are the ones that cover broad continent-sized areas. Think Antarctica, and think about most of the world at the time of the ice ages. Glaciers erode by plucking. So plucking rocks, this plucking is when rocks, stick to the bottom of a glacier, and we've talked about this. So you can have rocks and other debris that stick to the bottom, and that's plucking. And then those items that are stuck to the bottom can erode by abrasion. So they scratch and scrape the ground and the rocks below as the glacier moves. And this is another example. We had one a week or two ago. We had a picture of a good picture of glacial abrasion, and this is another great picture of evidence of glacial abrasion. And then we have what happens when a glacier melts. So when it melts, it leaves behind everything it was hauling. And the sediment is called till. So if you ever think about like an old time plow, like the kind they used to pull on oxes or stuff, and sometimes people pushed them, it's like a big blade that just kind of, well, plows through the earth, and it moves the earth that it's being driven through off to the sides. That's tilling, right? Well, this is till. So it tends to be a lot of unsorted sediment, and it just sort of gets it gets left behind when the glacier melts, but it also gets pushed out to the sides as the glacier moves, just like we were talking about how an old school plow would till. And this is all unsorted sediment. You can tell because it's, there's big rocks and little rocks, and they're all kind of mixed up together. It's not got the biggest ones on the bottom and then the smaller ones on the top. And there aren't clear layers here either of deposits over time. So one type of glacial erosion is a cirque, and that's when you get this scooped out depression, and they come from valley glaciers. So this area here is a cirque. And then you can also get a hanging valley. So this happens during some sort of specific glacial movement. So you have two glaciers that meet and retreat. Retreat can mean either the end part of the glacier has moved along, or it's kind of melted away in an area. So probably what happened here is there was probably one glacier that came this direction and one that came this direction. And this one had cut in here, and this one was cutting in here. So you have this U-shaped valley, so you know it's a glacier, not a river, but there is water up there, and it's coming out of this hanging valley down to below. Hanging valleys are a good place to look for waterfalls. So here's a moraine, and this is an unsorted ridge of till. So that previous picture when we talked about till, that maybe perhaps was a moraine at one time. So you have this, or it could just be an outwash plain, which we're going to look at too in just a second. So you have all this unsorted till, which we talked about before, and it's just ridges and ridges of it. And this one here looks like the kind that comes off the side of a glacier. An outwash plain, which is what we have here, this is at the leading edge of a glacier where it melts and flows out with its deposits. So the leading edge would be like the front, if you want to think of it in the direction it's moving. And as it melts, all of its deposits kind of spread out everywhere. Now, the leading edge of a glacier can continue to move, but it can also, the leading edge can move back as it melts, if that makes sense. As the glacier gets smaller, the area it covers is smaller. So the outwash plain, which do tend to be in big flat areas like this, is where you see all of the deposits and stuff that were caught up in the ice kind of get tossed out into this plain. They melt out into this plain, and they land kind of everywhere. So this is why we get rocks from some parts of our geographical landscape that are transplanted to another part of our geographical landscape, and it couldn't have been by water because they're too big of a rock. It's typically because they were moved by a glacier. So these are some really cool structures that glaciers can leave behind. So these are drumlins, and these are these big elongated landforms where a glacier is going to move over an older moraine. So you have a moraine where you've got like the till on the side, and then a glacier moves over it and it kind of picks it up, moves it a little bit, smushes it down, and you get these interesting landforms that are called drumlins. Another kind of landform is an esker, and this is my favorite. So these are long, winding ridges of sediments, and these come from streams that flow underneath the glacier. So you've got a giant, 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 huge block of ice, and underneath of it, you have a place where the water is flowing, and it makes like a little stream where the top of the stream is touching the glacier and the bottom of the stream is touching the earth below. And it will pick up sediment as it goes, and it will drop sediment, and it will leave. You can almost imagine that if the glacier fit over top, it would leave like a little space for your stream. But a lot of this stuff will get picked up in the ice as it flows, and then it'll either get moved along and dropped, or it'll kind of melt there, and you end up with this really cool, long, snake-like, it's almost like a little wall created from sediment, and that's an esker. And then you also have a kame. A kame is this conical mound of layered sediment, and it's deposited at the retreating edge of a glacier. So that's the back end, if you want to think about it directionally. And this just tends to be where they kind of like leave chunks behind, and that's where you get a kame. And then glacial lakes. And who doesn't love a glacial lake? This is the type of lake that's formed when a glacier erodes the land and then it melts and it fills the depression. And if you look right here, there's some alluvial fans that are really obvious. And if you look right here, you can see a U-shaped valley right here. So this is where a glacier came through. Clearly there was glacier here. And this right here is a hanging valley right there. And you can see there is a little waterfall coming out of it. But this area right here, this would be your glacial lake. And they're usually really pretty. They can be really blue, and they do tend to be up in the mountains. Kettles, these are formed by depressions made by a block of ice that fell off of the glacier, and they tend to be in more level terrain as opposed to the glacial lakes, which tend to be up in mountainous areas. So a huge chunk of ice that moves over land is a glacier, and you can have valley and continental glaciers. Glaciers pluck rocks that they pick up as they go, and they can abrade the surfaces below with sediment that scrape the land that has been plucked. And then it is true that glaciers make valleys wider and scrape away the sides of a mountain. So let's talk about waves for a minute. So waves are most commonly caused by wind. So wind-driven waves or surface waves are created by the friction between wind and surface water. As wind blows across the surface of an ocean or a lake, the continual disturbance creates a wave crest. That says crest, although it's just barely out of the screen for you. So as the wind blows, it will push the water all in one direction, and it will create a wave crest. So you can actually create this effect on a smaller scale if you blow across your bowl of hot soup. You can make tiny waves. Or if you really concentrate the moving air by using a straw or whatever, you can blow water across the top of a bowl, or, I mean, anything. If you're in a swimming pool, you can blow in front of your face and you can create small waves. So basically, this happens on a much, much larger scale in big bodies of water, and this is how you get waves. So ocean waves carry energy across the ocean. Ocean waves affect only the surface of deep water, which is true. And as the waves get closer to shore, though, they drag on the bottom. So here we have waves shaping the coastline, and they do this by eroding rock and transporting sand and sediment. So this is what we call a headland. And a headland is where you've got a coastline, where you've got waves, and they meet different layers of hard and soft rock, but they're perpendicular to the sea. So the headlands are the resistant rock. So basically you've got waves coming this direction, right? And they've smacked into this coastline for some time. And as they do, they will erode the softest rock. And when they get to the hardest rock, they're having a harder time. And that's because this is going perpendicular, not parallel. This way is the water, this way is the land. So perpendicular to the water, and they basically make like a big wall that the water can no longer get through. So when you see cliffs along the coastline, those are a type of headland. So part of a shore that sticks out into the ocean is called a headland. And the major cause of erosion along coastlines is waves, and waves that carry sediment cause abrasion. So how do waves shape the coastline when they deposit sediment? Well, they form beaches, spits, and barrier beaches. So a beach is made of sediment, which is usually sand, and it's at the water's edge. It's been deposited by the water and by waves over time. And then you have what you call longshore drift. And this is when the waves are not hitting the beach at like a perfect perpendicular angle, but rather at a slightly more acute angle. So instead of the waves coming right straight at the land, they're coming kind of this way. And you can see how they did. You can actually see, that's why I chose this picture because it's perfect. You can see the shape of the wave. So it doesn't hit like, it's not a perfect arc going this way. It hits at sort of an angle, and you can tell they've created these little ridges. Well, over time, as the waves continue to hit this land here, they're not going to make the exact same mark every time. They're actually going to hit maybe one, the center of one will hit here, and it will cause this pile of sediment to spread out, but more in this direction, because you can tell the waves are coming at this angle. So it'll start to push over time the sediment this way. And it's what's called longshore drift. Now, they do use multiple types of erosion control methods along beaches that are used for recreation to control longshore drift. You may see them as little fences that run kind of perpendicular to the water across the beach. And they do that to try and keep the sand from just moving past the area that people are using for recreation. Now, a barrier beach or barrier island is this long, narrow island parallel to a body of water, and the water between the island and the mainland is called a sound. So you may recognize this. You may have seen it on a map before. This is the Outer Banks in North Carolina. So this is a very popular place for holiday vacation. You have like Nag's Head, Kitty Hawk, all that's here. So this area here is the Outer Banks, and this is your barrier beach, barrier island. And this would be your mainland here and here. This is where this is actually a piece of the mainland. It's attached up there. And so this area in here and in here is called the Sound. So out here, you get all the ocean wave activity. And in the Sound, you don't have the ocean wave activity, but you do have water flowing as a general rule. Like you see, this water is a river. It's coming out. You can even see how it's circling around this way. And this water is coming this way, and it's all headed out there. So the Sound is a much more peaceful place if you're going to have like a beach house or something, because you probably won't have big waves smacking into your property. Of course, it's going to be at a good risk for hurricanes, just like everything else that's along the water. But it's also forms a very important ecological area because wildlife that thrives in salt water that can benefit from a lack of pounding by waves and constant movement can really grow in an area like this. You get a lot of wetlands, and there's a lot of really interesting wildlife that live in places like that. Now, this is a spit. This is if a headland stops longshore drift, if a headland stops longshore drift, and then your sand piles up and it starts to form what we call a spit. So we had some drift going probably both directions here. And then for some reason, something under here is pretty hard, some hard rock in this area. And this is probably just sand, but the hard rock's probably back here a little further. And so the sand is going to wrap around, it's going to form this big, long finger-like protrusion into the water, and that is called a spit. And now we have sandbars. Okay, so sandbars are these ridges of sand, and they're deposited by waves running parallel to the shore. This is kind of like the beginning of a barrier beach, barrier island kind of deal, but these don't last. They tend to shift around too, depending on the behavior of the ocean and the waves. So sometimes they're smaller, sometimes they're bigger, sometimes they're slightly moved. But this is a good one here. This is a good big sandbar, and they're fairly well packed sand. So as you can see, people just pulling their boats up here and they're just having a party on this little sandbar. And you know, why not? Looks like a beautiful day in a beautiful place. Hang out on the sandbar. So your barrier beaches are long, narrow islands parallel to the shore. And they're called barrier too because they do kind of protect from the ocean, if that helps you remember it. Your spit is a beach that sticks out into the water like a finger. Longshore drift is the movement of sand down a beach by waves, and a sandbar is your long ridge of sand parallel to the shore. So wind erosion, I'm going to leave this screen here for just a minute because, well, you know why. I don't have to tell you why I'm leaving it. It's obvious. This is my favorite GIF I've ever found, I think, at least for use in a slideshow. Whoever did this is my hero. All right, so wind erosion, we've already talked about surface creep, saltation, and suspension. And these are our different types of wind erosion that we've discussed already. So some of this is review. Now, the results of wind erosion would be something like deflation. And if you think about a balloon just deflating and shrinking down, that's exactly what happens to the land due to the wind removing surface particles. And this little hole is an example of deflation. It's not always a hole, but this hole is a really good one to see. And the wind was moving in some kind of a circular pattern here, and it just kept whipping out pieces of sand over time until it deflated and made itself a nice little hole there. Now, abrasion, we talked about this with the water. Remember, we talked about how water and wind are both fluids, and abrasion of suspended sediment in water can smooth out the rocks. And here you have abrasion from sediment or sand that's suspended in air, and it is just like sandblasting. Whereas with the water, it was kind of like sandblasting, but it's sandblasting with water. In this case, you're sandblasting with air, just like you would. And what's left behind are called ventifacts. So ventifacts have been worn, polished, or faceted by wind-blown sand. So look over here first. You can see here these big rocks sticking out, and then there's this here, and this area here, this area here. These are all potential future ventifacts. As the wind continues to deflate this area, these particular rocks will become shaped by the wind, and they will be ventifacts. And this one is particularly interesting because you can see how the wind is cut in here and here with the sediment. And then it has this very, very specific sort of cylindrical shape, which almost makes me wonder if there was some sort of like igneous vent or tunnel that allowed the magma to cool in this particular shape, because that's really interesting. But you can see some amazing ventifacts in Monument Valley and other places. They do tend to be in drier areas, and that's because when you have less vegetation to hold down your sediment and sand, it's going to be picked up more easily. Plus, there's less rain, and that again leaves a nice top layer of sediment or sand that can be moved away with wind more easily than it would be if it were packed down or if it were wet. And then you have also, those drier areas have sand and not dirt. So then you also have, dunes, and dunes are piles of windblown sand. And these are the types of dunes you find in a desert area. There are also dunes along a beach. If you're ever visiting a beach and you see the dunes, very often they'll have a sign that says to keep off them. And that's because they also form they have a very important ecological job there, and they provide an environment for certain life forms that don't do well out on the wide open beaches, and also because they protect inland structures. So they're often held in place by things like seagrass. So it's just very important, if you see them, to leave them alone and let them be. They will shift and change over time. And so will these ones in a desert situation. They would just constantly move around. It's always a different shape. So the process by which wind picks up sediment from the surface is called deflation. And wind erosion occurs by deflation and abrasion. And that's it, you guys. I hope you have a wonderful week or so without me, and I'll see you when I get back. Miss your faces.